Hello everyone, and welcome to the first online consultation of computer graphics. And in this lesson, actually, I'm not gonna do anything regarding consultations, answering questions and everything. I'm gonna do really hitting on your heads, brains, whatever you would like to call it, and lecturing you about the principles of computer graphics. Now, of course, feel free to ask questions right away. Interrupt me like, Mohammed, I don't understand this part, or this part doesn't make any sense, or something like that. Just please feel free. Immediately just come in, ask the question, and say, okay, just pause here. Let's repeat that part, or let's rehearse or reiterate on that part, so we can all follow, the whole thing easily. Now, computer graphics is a branch of computer science, and computer science, some people can consider it as a branch of mathematics. Computer graphics involves a lot of math. I mean, at least the programmable part, not the artistic part, but the programmable part is involving a lot of math. So, the amount of math in computer graphics is really easy. I mean, not that very much complicated. If you know how to subtract, add, divide, and multiply, you are actually going to go through this really easily. I mean, a little bit of knowledge, of course, of linear algebra would really help a lot. However, throughout this course with the professor, you will actually get the linear algebra kind of theory part, and I will give you the practical side of what professor was talking about during his lectures. So all the vectors, matrices, multiplications, and all these stuff which professor was doing on the lectures, you're gonna see it applied in the exercises and workshops. So this is actually good to mention here. Now, there are many questions regarding how an object is being displayed or actually being rendered on our screen. Okay, how we can get a simple 2D or 3D object comes in and just being represented as a glowing pixels on our screen. Okay, and there are many, how can I say, steps involved in getting any 2D or 3D object just being, just converted to a glowing pixel on your screen. First of all, the first question is being asked: how can we represent 2D or 3D object in computer graphics in general? How describe a 3D object? So imagine this for the following: when you're trying to describe a 3D object or a 2D object for that matter, usually you have to have a coordinate system of some sort. And apparently I had a large x-axis a couple seconds ago. Let me try to draw the other axis. Hopefully the computer will let me. Now, this is, let's say, the x axis, and this is the y-axis. Somehow my computer is still not responding. I think my recorder is somehow interfering with this really hard. Okay, let me see. Can I get the mouse here? Let me see here with E and erase this. B again. And this is the y-axis, okay? And if I describe a triangle, let's say this is part here 1, this here is 1, and let's see, here's 1. You have first to define a coordinate system, okay? And a coordinate system is needed so you could actually put a point somewhere, on a certain position on a grid. So there you go. So let me, unfortunately, somehow I cannot get easily. Oh, let me actually, how about this? Let me try to get a different color for you. Maybe some sort of red or something like that, so it can be visible, shining through. So let's say we're going to describe a triangle right here, like this. Okay, and let's say this is point 1, 0. Oh, sorry. X comes forward. 0, 1, 1, 0, and this is -1 and 0. Okay, and we convert 2D into 3D. Just this is a question apparently. We convert the 2D into 3D by adding it width and height. Convert 2D into 3D. Actually, the width and the height is 2D. The depth is the 3D part. Okay. Or yeah. So this is yeah. So basically, width and height is 2D, and 3D is the depth right now. Okay. So I will actually give it a try again with the tablet. The tablet doesn't allow me to draw anything, unfortunately. It just doesn't. Now it responds. This is great. Okay. So this is how you describe an object. You first describe first a coordinate system, and then you draw based on this coordinate system. Now, computer graphics, we always love triangles. We always love to convert any 3D object and work with it as triangles. And there's a very, very good reason for that. The first thing is triangles are the simplest polygons, or a simplest kind of geometry ever, because they are just they are consisted of or composed of 3 vertices or 3 points. You have just only 3 points, and you describe a surface. Okay, so for example, by the way, this is here. These points, these guys, are called vertices. So the singular version is vertex. This is the singular, and plural. So plural is vertices, not vertex, not vertexes, but vertices. Okay, this is very important. And you're gonna get this term a lot, by the way. Nobody's using points. They are just talking about vertices all the time. So there's the first reason. They are really the simplest forms that you can make a surface out of them. The second reason is they are always coplanar. What does it mean by coplanar is that they could in fact lie on a single surface no matter how you are actually rearranging those vertices. So if I bring up Maya here for a second, and if I try to describe a triangle here, let me go ahead into the top part here. Let me see. Somehow I cannot. Okay, here's a triangle. And let me just put it in the shading mode. And right now you have a triangle here. And no matter how you rearrange this triangle, all of the points, all of the plane is lying on the same plane. Like all of the points are always lying on the same plane. You see? They're always on the same plane. And this is very, very important, and this is very good, because this makes it easier for whoever is working for the computer when it's working on, or whoever is working with lighting conditions and calculating how certain render of a certain faces are going to go based on how the lights were going to be bouncing off these faces. It makes it a lot easier actually to compute, and a lot faster in fact. And as you can see, I'm keeping rearranging my vertices. No matter how I'm rearranging them, they are always lie on the same line. You see, if I just rotate really nicely, I get this single line almost, so they are always on the same line. Unlike quads or polygons that are composed of four how can I say, 4 points or 4 vertices. Okay, so if you have a quad like this, and if I start actually just to move one vertex, right now this is not a normal polygon anymore. It's something weird actually. It's not. I mean it's broken somehow into 2 triangles anyway. But when you look at it, it's an actual quad composed of 1, 2, 3, 4 edges. And as you can see here, I could rearrange them in any way, and in some cases they will not be planar, and this could cause a lot of glitches and a lot of problems, and you don't want this actually to happen to your game or to your interactive application. So that's why people tend to approximate any 3D object into triangles, and it's actually, in fact, any 3D object in the universe, I think, could be approximated into triangles. Any 3D object could be done in triangles. I mean, even if I bring up a sphere, and if I go over here and say triangulate somewhere here. Here's the sphere. It is circular, right? It's actually spherical, right? So there you go. However, it's broken up into many triangles. Any 3D object could be approximated or could be represented into triangles. Okay. Another reason as well for why we love triangles as well is because not only that the GPU is dealing with them much faster, but it's quite easier for the algorithms to start modifying in real time the objects. So you could subtract a lot of triangles in a way that you can still keep the outer shape correctly. So for example, you have a huge world and you have huge mountains like in the backdrop, like mountains that are really far away from you. Now, of course, the mountains have a lot of details. They have a lot of rocks, they have a lot of mini rocks, and they have like stones and all these stuff. Mini rocks. What a word. If this word exists, I would be wow. But anyway, you have stones and rocks, and huge chunks of rocks are laying in there. And all of them require a huge amount of triangles to describe them. Now, the problem here is if you are really far away, being 1 kilometer away from the mountain and 1.5 kilometers away from the mountain doesn't make any big difference in terms of details for you, is it? You will still see the mountain with much less details. So it is actually quite feasible to subtract, to reduce the amount of triangles being displayed, being rendered, while keeping just the shape of the mountain. The closer you get to the mountain, the more triangles we're gonna add. And this is the problem of which most people say it's for the short LOD, or level of detail, controlling the level of detail. Okay. So that's why people love more triangles. You could like subtract and add triangles more to, or tessellate the object, make it a little bit more complex, reduce the complexity, and so on and so forth, to achieve the same object shape. Now, if you look at from the modeler's point of view, like if you are doing 3D modeling, you're going to hear me always all the time talking about do not have triangles in your objects, do not have triangles in your objects, always have quads. You see? And why is that? Because it's much easier to control quads than triangles. If you are dealing with, right now I have 2 faces, is it? This is face 1 and this is face 2. Okay? With quads I had only 1 face. I had just only 1 face, not 2 triangles. It's much easier for animation. It's much easier for controlling any kind of anomalies which comes out, for example, when you are doing 3D models. It's also very important to have quads because when you convert your polygons to triangles, you could run into problems if your polygon of your 3D model composed of either a mix of triangles and squares or quads, or a polygon that is composed of more than 4 edges. All right. So it is very important that you be careful when you are actually doing a 3D model. You have to keep everything consistent. Everything should be like in polygons, in quads. Sorry, so poly quads. Okay. If you look at 3D sculpting softwares like ZBrush or I think there was another software called I think it's called a sculpting software. I forgot. Sculptress. There you go. So this is another software as well that deals with everything which deals with it. It deals with it in triangles as well. Okay, so this is very, very interesting software. Maybe we're gonna see it some other lesson. Okay. Now, since we know how we describe our 3D objects, how we describe them, and why we love triangles. Okay. Also, let me get back to the blackboard here, or blue board for that matter. Let's talk about the triangle winding. Now, winding means how your 3D object is represented in terms of the order of drawing vertices or the order of defining vertices. Now, it's very important to understand whether a triangle like this, you know, pointing towards you or pointing away from you. This is very important. Why? Because you don't need to render something that you won't see anyway, right? And this is which people have some problems with Unity in the first time when they start modeling their objects. They make a car, for example, and then they send the car to Unity. They import it inside Unity, for instance, or any game engine. Most of the time they have this face culling feature where they see any face that's pointing away from the camera. They just simply discard that face. They say this face is rendered away from the camera, or it points away from the camera, so we don't need to render it. Now, how this is in fact is happening. Now, if this is our 2D axis, if you would like to add a third one, oopsie, sorry about that. And let me try to, you have to add a line perpendicular to these two axes. Now, this is negative z, this is positive z, this is negative y, this one is positive y. Okay? Positive, negative x. And this is the positive y. Sorry. Okay. Positive x here, negative x there. Okay. So most of the time you will find out that whatever is pointing away from you is going to the negative z, and this is pointing towards the positive z. Okay. Now, in order to describe a 3D object, I just simply let me put here one more point so you could understand the part of triangle winding here. Maybe I should have added a little bit of depth here. How about this? I'll define a point right there, and one more point right, one here and one right there, and one here and one right there. Now let me grab another color for a second here, and this is gonna be here and there, here and there. Now, of course, this face, the face which is lying here, is kind of It's kind of obscured, but let's skip on that for a second here. If I define this as a, this is point A, this is point B, and this is point C, D, and point E, okay? And if I'm trying to define here the vertices, so I'm going to say, I'm going to give the computer certain instructions, and I'll tell the PC, okay, grab the first 3 points, which I'm going to give it to you, and make up a face out of it. So it will grab this one, for example. So I say, grab the point A, B, and C, and draw a triangle. Now the question is here: should I pass it as C, A, B, or B, A, C, or something like that? Should I pass it like starting from here, going all the way around to here, or shall I start from here and go all the way around to there? Now, as a matter of fact, it doesn't matter very much. Okay, what matters here is you have to be consistent. Okay, so if you chose to go and draw a triangle based on a certain direction, you have to really say, okay, I'm going to draw the triangle, for example, counterclockwise, to define triangles that are facing towards me, and clockwise way is for triangles that are facing outwards or away from me. Okay. Now, this is actually most of the time this is the standard. People usually say, okay, anything which is counterclockwise is for triangles facing towards me, and clockwise definition of a triangle is that for the triangles are away from me. Okay, so counterclockwise. So counterclockwise means that I'm going to have to go this way, right? So I'm going to have to define a triangle. I'm going to call this CAB. So this is going to be my first triangle. Now, of course, you're going to plug in the CAB. So because C here is like how much? Is 1 in X, 0 in Y, and 1 in Z, right? B here is -1 in X, 0 in Y, plus 1 in Z, right? Okay. And here E is lying, in fact, on the x-axis right here. So I'm going to leave it as it is, which is going to be -1, 0, 0, because it lies on the 0 here. Okay, it doesn't exist on the depth, it doesn't exist on the -z yet. And for D, it has this coordinate of 1, 0, 0, right? Now, the first triangle is going to be like C, A, and then B, okay? Now, the next triangle, counterclockwise, we're still counterclockwise, and it's going to be DAC, okay? So D, A, and C. And if we rotate this guy, if we look from the perspective of this side, we're going to have counterclockwise is going to be E, A, D, and then we're going to have here, from the point of view of this guy, B, A, E, B, A, E. Okay. Now the question here is, it says, okay, what's going to be when you pass in these instructions to the computer, it will ask, okay, how I'm going to render these stuff. So you say, okay, render me the first face. So the computer will test, okay, C, A, and B. This is counterclockwise? Yes, that means that the face is facing towards me. That means we're going to draw this triangle. So it goes ahead and it just draws this triangle for me. And you get it as glowing pixels on your screen. Now, the second question here, it comes to the next guy. So D, A, C. Are we still counterclockwise? We are. So it says, okay, we're going to render just this triangle, like this. All right. So, and let me just undo that part so you can see. And now it says, okay, what about the E, A, and D? Is it counterclockwise? So it says, it sees like this. E, A, and D. It is in fact a clockwise. So it says this face is facing outwards. I don't need to render it it will just ignore it. And this is how the backface culling works. Okay, it just sees the order of the vertices, and it just simply says, okay, if this face is pointing away from me, I'll just, just ignore it. If the face towards me, I will need to render it. Okay, and this is very, very important that you know about this, and you have to remember this, because if you're gonna work with game engines like Unity, like maybe like CryEngine, UDK, or any other engine for that matter, when they see a polygon that is being flipped, the normals are being flipped. That means that it's actually facing outwards instead of, or inwards instead of outwards. It will just not render that polygon, and you will end up with 3D objects that's full of holes in it. Okay, so you have to be careful about that part. All right. Now this is all about the how we are actually defining a 3D object and drawing it into our application. Okay. Now, are there any questions regarding that part before I move on to the next piece or next part of the class? Guys? All right. So is it clear for you? Do you understand what I was talking about 100%? Imad, trolling achieved. Thank you very much. Elvir, come on, man. This is nothing heavy until now. No, nothing is difficult in this part. The only thing is, which I advise students, is really come with open mind, because in computer graphics it's not like the other subjects which you were learning throughout the years before. They don't. It's a little. You have a different approach to a lot of problems, I mean, you get. You're gonna find solutions to your problems in. And trust me, it is. Yeah, you're saying it's simple until now, and it's really simple until the end. The only thing is, just don't be scared about it. The only thing is, the difficulty arises when you start looking at problems, and then you don't find your solutions on the internet, and then you start asking on the forums. This is where the difficulty starts to rise, because most of the time you are faced with the specific problems that are specifically pointing to your application of your idea, which nobody is implementing, let's say, in the outside world. It's not common that somebody will take your idea, implement it, and put the problems on the internet, if you know what I mean. So that's why this is where the problem a little bit arises when it comes to working in graphics. At least the programmable side of the world, maybe. That's why there are a lot of forums and people are helping out and everything. Well, of course, Imad, of course, everybody, if you have any problems, just feel free to email me. We can have a video chat. If you want, I can actually, we can use Link, TeamViewer, whatever, so we can, I could control your PC from far away over the internet, and then I could help you out doing 3D models, or help you out in your application if you are stuck, so. Thanks, man. Yeah, because I know Maya, but feel free to use any tool which you want. For the modeling part, yes, for the modeling part, I'm gonna use Maya because this is the software which I know. Feel free to use your own software. If you know Blender, excellent. You can use it. If you know SketchUp, if you know Cinema 4D or 3ds Max, feel free to use them. You have total freedom of using any tool you need to get. Yes, you can use SketchUp if you want to, but the main thing is deliver something good at least. By the way, it's not about the tool. It's about the person who's sitting behind the tool. This is very important, because I could produce a 3D object in Maya, And somebody could produce, for example, somebody could produce in SketchUp the same 3D object as well with the same quality. The only thing is who is sitting behind the tool rather than the tool itself. Now, of course, the tool plays a huge factor, which is, for example, helping you out solving certain problems faster or slower. It doesn't matter. It actually, the tool plays a factor in your production, but it will not play a factor in your imagination, or it will not play a huge factor in your it will not hold you back in implementing your imagination, I think, whatever you're imagining. So the sky is the limit, basically. And since Fit has already an agreement with Autodesk right now, you can just go with your student account and just EduFit student account and get registered there. You can get Maya for free, full version, student version, and you can play with it, do everything with it. What is the next step after finishing 3D models? We do start implementing applications, but this is, we can leave this for, you know, later part. Let's get the stuff. Let's get the stuff first. Let's get the basics on first, and then later on we're gonna talk about how we can make cool applications and everything. But we have to really understand the basics first. All right. Okay, so let's carry on and talk about the basics of coordinate systems. Now, in Unity or any game engine, and especially in computer graphics, a lot. I mean, I'm mentioning most of the time graphics engines and game engines most of the time because this is the stuff which you heard a lot about, you know. But basically, in computer graphics, you're gonna hear a lot about local coordinates or object coordinates for that matter, and world coordinates. Sorry about, oh man, hang on a sec. Sorry about the bad handwriting. The tablet is actually, my disk face somehow doesn't allow me to put the tablet in a much more comfortable pose. Coordinates, okay? So what is, in fact, what is the difference between them? Okay. If I define a triangle, and I will grab, in fact, a 2D triangle, because it's going to be a lot easier for me to define it that way. Because if it's 3D, I'm going to have to draw a lot in, and we don't have time for that. I mean, we don't have time for that. Okay, and there we go. Okay, and let's say again, this is the y, this is the x, and this is 0, 1, and this is 1, 0, and this is minus 1 and 0. Okay, so these are my 3 points. Now, if you look at this carefully, I have defined a triangle according to its local, some sort of frame of reference. I defined a frame of reference, and I have made up these 3 points, right? Even though the position of this triangle, according to this sheet, or according to this blackboard, blue board, whatever, is completely different from these guys, is it? I mean, if I draw, if this is my world, if this blackboard is my world, and I define a different coordinate system like this, okay, this is the y, this is the x, and this is my world. Right now, this is the world coordinates, and this is the local coordinates of my object, is it? I mean, of course I had to, if I didn't draw this, if I didn't define these huge axes, which defining my world coordinate system, you will always think that the triangle exists just only here, is it? And it's very important that you start, that you understand the concept of converting from local to world coordinates and getting back again. Because It is really essential for you so you could get something rendered on your screen. Okay? Now, it is exactly the same thing which I was mentioning during the regular classes. I was talking about always defining a building when you are building your own house, right? You are saying, okay, this is the piece of land which I'm having, and I would like to run from here till here, make a wall, from there to there, make a wall, and I'm gonna say these 2 meters or 10 meters across. Okay, so I'm gonna make a wall here 10 meters across, and then I'm gonna run from here to there 5 meters across. You know, and for you this is the measurement. You didn't take the GPS coordinate of this point and GPS coordinate of this point, and you then tell the builder to say, okay, from this GPS coordinate this point and this GPS coordinate of this point, you're gonna have to make me a wall. You don't do that, right? You just simply say, okay, from this point 5 meters to that point. You described your building or your house according to your local frame of reference. Okay, it is exactly the same thing which I've done to this triangle. I've defined a local frame of reference, and I have made a triangle, and I said, okay, from this point to this point, just run 1 unit, right? Sorry, just a second. So just run 1 unit and put a point here or vertex here, and from here to there 1 unit, and from here to there 1 unit. And you defined a triangle from a local point of reference. All right. Now, why this is important? Why we have a local? Why don't I define a triangle according to this world coordinate? Which, let's say, if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then run away again. 1, 2, oopsie, let's make it a little bit bigger. 2, 3, 4. Not consistent here, but bear with me. 5, 6, 7, 8, 9, 10. And according to the world, let's look at this. According to the world, this coordinate is going to be, oh man, why I didn't write the number? 5, okay, 10, 11, 1, 2, 3, 4, 5, 6, 7, 9, 10. Sorry about that, guys, just bear with me here. And 15. Now, I can count. Now, this coordinate, this part, is, according to the world, is 8, sorry, in y, and let's say approximately 10 in x. This is 13 in x, and about 8 as well in y. This guy is, let's say, 9 or 10 in y, and let's say 11.5 in x. And then you get, and then you have got this world, this definition of this triangle in this world coordinates. Now, how important this concept is, why we need to know about this. Let me for a second, you know what, let me see. Okay, great. I will in fact select this, you know, and Control T. What happens if I just rotate this 3D object like that? You see what I've done there? Right now, locally, according to this 3D object, when I rotated it, the y-axis is pointing here, okay? The x-axis is pointing there. You see the problem? Now, here's the interesting part. You're going to have to answer the question whether I will move this triangle according to its local coordinate system, or move this triangle according to the world coordinate system. If I say to this triangle, move up, which up are you meaning? Do you mean up for this guy? So it will go in that direction? Let's start to joke with me again. Okay. Sorry, hang on a sec. Let me just erase this. So when I said again, move up, whether it's in this direction or will you move up towards that direction according to the world. Okay. And this is which people are a little bit having a problem with unity, let's say. They define a car, it's like a car in real world. If I have a car like this, and this is the engine part, this is the front side of the car, and this is the back side of the car, okay? And if I say to the car move forward, it will move forward like this. Once the car rotates, oopsie, sorry. Again, somehow I start getting this glitching again. So if the car rotates like this, and this is the engine part, and this is the back of the car, and we say to the car move forward, it will move forward like this. It will not move like this, of course, but it will move that way according to its local coordinates. Okay? So this is very important to understand, because sometimes some people in Unity, let's say, they rotate an object and they tell the object to move forward, however it moves left or moves right or moves somewhere else. It doesn't move forward, and this is because they are moving it according to its local coordinates. So it's very important to understand that concept, the difference between world and local coordinates. Do you guys understand this part? Do we understand this idea? Do you have any questions regarding that part? Anyone? Okay. Now let's move on to the part where we are talking about basics of transformations. I'll go ahead and erase actually I need to keep that coordinate system. In fact, you know what? I will just draw this and delete. I don't need actually to start erasing like a whiteboard. Okay. Now let's assume for a second that you would like to transform. So this is -1, -2, -3, -4, -5, and -6. Let me move this center just a bit, and let me press here a button and go there. Okay. Now, looking at this coordinate system, if I have a triangle, let's say, okay, I have a really big numbers, but okay, and I will move. I will actually position these points right here, and I would like to move this triangle somewhere else. Now, when you are moving a triangle from one place to another, you need to add to it. You need to add to its coordinate system a certain number. So it's an additive operation. So if I would like to get this vertex or these vectors, I need just to add to them. So for every vertex, so that I can start moving this triangle towards this way. If I start subtracting them, subtracting these numbers, I will actually move the other way around. Okay. If I would like to scale it, I have to start multiplying it. Multiply by these three numbers, multiply by these coordinates, any vector, and then you will start getting a larger version of your triangle. If you would like to rotate it, you have to use trigonometry to start rotating your triangle either this way or that way. Now, unfortunately, my coordinate system is really big, so I'm actually going to get a smaller one with a smaller scale. And let's hope that my history actually is quite big, so I could undo, and I cannot undo that. So I'm going to actually erase this with, sorry, let me Control Z that. And I will create a new layer here, take out this one. Let me put here my, actually, you know what, I need to, okay, I need to define that layer again. I undone more than I should. And I will make it really simple here. I will use very simple numbers, because the larger the numbers you use, the more complex the numbers are gonna get. So I'm gonna just put here, I'm gonna exchange the numbers here. I'll put one red, another point, here's my point, another point, maybe a little bit more, here's one more point, and there we go. And let's imagine for a second that this is 1, 0, and this is 0, 1, and this is -1 and 0. And this is the same problem which I worked on during the class, and I think it would be, I think it will suffice very much to present at least the idea. So let me just put here y. So this is the positive y, and this is the positive x, and this is the negative x, and we are good to go. Now, if I would like to scale such an object, let me just push this aside here. If I would like to scale such an object, for let's say I would like to, or at least translate an object. Let's say let's put translation first. So if I would like to translate this object, translate this point, at least, I will define it like this. I will say 0 and 1. I will define it as a vector, okay? And vectors, usually people sometimes they like to define it like 1 and 0, but I usually like to define it like in a vertical way. It's much easier for me to see, honestly. But this is, again, it's a personal thing. So let me just get this a little bit more in a beautiful way, so or just refine my line here. So 1 and 0 for x and y, and I will add to this position just by 1. I would like to move it nothing in y, but 1 unit in x, and the result is going to be like 1 plus 1, so 1 plus 1 is going to be 2, and 0 plus 0 is 0, and at the end you get a new point right here, okay, which is going to be, actually, let me try to add one more layer over here. And I'm gonna call this new triangle. Yes, Ahmad, yes, I did. And I will go over here, and I'll change this to another, let's say, more like yellowish kind of a color, so it would be a little bit visible. So I think it's visible on this whiteboard. Great. I'm actually gonna add it. Let's see if I can edit this as a swatch. So I'm gonna call this yellow pen, whatever. So and then I have here a point, so it's gonna be 2 and 0. Okay. And if I keep going on every vertex, because this is actually the operation which is really happening in the real world, I mean, not the real world, okay, in the real world as well as on your computer, this is actually what's happening. It goes for every vertex on your object and starts moving it one by one until you get the object completely translated from one place, boom, into another place. So let's go ahead and let me get this. I will get rid of this red part, and I will, well, actually, I will add this as well as a swatch. I'll call this red pen, so I can just switch between them really quickly. So I can like dink, and I can move on. Or actually, I need this. Actually, this one, because I'm gonna add right now this point. So we have 0 and 1. If I add to it only in x-axis like this, or I just add this vector to that vector, I will get this 0 plus 1 is 1, 1 plus 0 is 1, and this is my new vector, which is describing a vertex at this point, 1 and 1, which is right here. If I get another vertex, I don't know why my lines are vertical, maybe because I'm holding the tablet in a very bad way. Let me try to get this in a better position so I can actually draw something a little bit normal. Oh, it's impossible. Okay, let me try to push it like this. So 1, and here I'm going to put here minus 1 and 0. There we go. Plus 1 and 0, which is the same vector which I'm adding. So I'm translating the whole triangle just on the x-axis, just towards the x-axis. And minus 1 plus 1 is 0. 0 plus 0 is 0. And again, I'm right now defining a new triangle, a new vertex right here. My new triangle is going to be this one. You see? So it's really that easy. It just you add to every point a certain vector, a certain vertex, and a certain number, actually a vector right now, and you get a new triangle at that position, or you get your triangle at that position. This is how translation is in fact working. Okay, now how about scaling? We would like to scale. This is called, I'm going to call this the translated new triangle. I'm going to add one more layer, and I'm going to hide this one like this. Actually, I was writing all the time on this layer, but anyway, I'll hide this one, and I will have, this is going to be scaled new triangle. And now when we come to scaling, here's the interesting part. It's a multiplicative operation. Sorry about that. So how can we scale a triangle? So we say, all right, if I would like to scale a triangle, I would go ahead and I will grab every point, multiply it by a certain factor, and I will just scale it all out. If you would like to scale the triangle uniformly, so I'm going to scale it in x and y at the same time, I will just go ahead and define, I will go ahead and grab my vertex. So my vertex here at, let's say, 1 and 0, I would like to scale it twice. Alright, so multiply twice. You know, scale it twice in both directions. And I will say, alright, so 1 times 2 is 2, 0 times 2 is 0. Alright? So I got a new point, which is at 2, which is right here. Okay? 2 and 0. Okay. Let's move to the next one. Let's move to the next. That's a very long definition of a line, actually. Okay. I'm going to move into the minus 1 and 0. So minus 1, 0, times 2 and 2 is going to equal to minus 1 times minus 2. Minus 1 times 2 is minus 2. 0 times 2 is 0. and you get yourself a new point, which is going to be right, let's say here. So it's going to be -2 here, right? And then we're going to go ahead and I will say, okay, would like to scale the last point, which is going to be 0 and 1. Actually, Control Z, by the way. Okay, so there we go. Times 2 and 2, you get in 0 times 2 is going to be 0. 1 times 2 is 2. Hang on a second, sorry about that. And then we're going to have 0 in x and 2 in y. So 0 in x, 2 in y. So let's say we are trying to find a triangle somewhere right here. So this is going to be the position of 0 and 2. At the end you scaled a triangle and you got a new one, which looks like this. So you took a triangle, you scaled it twice, right? It's really easy, and it's very, 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 very straightforward. Now, I will not actually work out every single number in the next part, but I will work out on one only because we can get the stuff a little bit faster. So I'm going to put here rotated new triangle. And right here, when it comes to rotation, rotation is a little bit kind of interesting when it comes to this part, especially because you have to you're gonna have to utilize trigonometry. So the actual formula of rotation, as far as I remember, it was if you put here an x, so x prime, which is the new x coordinate, is equals to x times cosine theta plus minus sine, actually plus y times sine theta minus sine theta. Okay, and y prime is equals to x sine theta plus y cosine theta. This is the actual formula. Let's hope that I didn't make a mistake about it. This is the actual formula for rotating a 3D object. And please, for rotating at least a point, and then of course if you multiply, if you do this calculation for every point, you're going to get a new xy. How can I say? You're going to get a new xy coordinate, and then you can start rotating things. Okay, the proof of this formula actually exists. How we got this is actually I think the professor is already mentioning them, explaining it on the classes. So please follow up the materials on how we got this formula. Anyway, the proof of this formula, at least for your exam, it doesn't matter. But I mean, if you learn this small formula by heart, it's done. But if you are curious how we got this, just please follow the materials of the professor. Actually, if I start proving it here, it's going to take really long time, and we're going to go outside of the scope of why I'm actually trying to introduce you this thing. Okay, so now what I'm going to do here is start getting calculations. So I'm going to grab this point, let's say. I'm going to say, okay, the x prime, which is going to be my new x, is going to be 1 times cosine, and let's say I'm trying to rotate this point 90 degrees over here, so I'm going to rotate it like this. So I'm trying to rotate the whole triangle this way, so just 90 degrees, like in that direction. So cosine 90 degrees is 0. So cosine 90 degrees plus y is actually 0 minus sine of 90 degrees. I will actually rewrite this because sine 90 degrees is 1, and the sine minus sign here, then it makes it actually minus 1. So and I will just rewrite it again. So here equals to y prime equals to 1 times sine of 90 degrees plus 0 times cosine of, actually not theta, 90 degrees. Let me just undo this for a second here. 90 degrees. Oh man, this looks like a G actually. Sorry about that. 90 degrees. There you go. Again, sorry about the thing. The tablet position is kind of weird. Alright, so if I look at these guys are already gone because 0 times sine is 0 and 0 times cosine is 0, and you get at the end cosine of 90 degrees is 0, so this is resolved to 0, this is resolved to 1 because sine of 90 degrees is 1, and 1 times 0 is 0. Y prime sine of 90 degrees is 1, 1 times 1 is 1, and then you get a new coordinates, which is going to be, let me see here, switch, and your actual point is going to be right there. So this guy moved from here right there. You see? Right now you got the same exact coordinates as this guy. Okay? Now, of course, we can start doing the math for every one of them, okay? And at the end, you will end up with a triangle that looks like, let me see here, let me erase this part because this point will not exist anymore. You're going to end up with a triangle that looks like this. Okay? And this is going to be your new triangle when you start following just the math. Okay? So this is actually kind of cool, right? Now here's the problem with this. You see, I have to do, I mean, this is as easy as it gets, by the way. And you see this formula is really easy as it is. This is exactly the same formula which you're going to see in the matrices when you start multiplying them. Because the matrix of rotation is in fact exactly as this one, as far as I remember. At least for 2D, not 3D. 3D is going to be just slightly different. Okay, this is the actual matrix for rotation in 2D, by the way. And if you're going to do it on your tests, you're going to see the same one. Now, the problem is with oh, I cannot erase anymore. I cannot undo anymore. The amount of transformations here are too much. So, for example, if I would like to add, if I would like to translate, I have to add to the vertices, and then let's say for example, for instance, I would like to achieve all those three effects at once. So, for example, I have, I will just create a new layer. I'll call it what I want to do, because it's actually what I want to do. Let's imagine for a second that I would like to translate my triangle, rotate it, and scale it twice. So here is going to be, let's say, actually not like this, because the 2 was somewhere right here. Right there. And right there. So this is my triangle, scaled, rotated, and translated. Okay, so I moved it a bit here, like right here, and then I rotated it 90 degrees. Okay, and I would like to do this. I would like to do these 3 operations. Now the problem is you have to do these 3 operations 3 times. So you say, okay, first we translate. So you multiply. So you actually add to every vertex another, or for every vector, or for every vertex another vector, which moves this triangle according to the x-axis. For every, if you would like to scale the triangle, you have right now to go to the next operation, which is another transformation, scale. You start multiplying every vertex, and you scale your object. And then you would like to rotate, and then you start calculating your cosines and sines and everything, and then for every vertex you multiply this vector by this number, or by that matrix, whatever, and then you get the rotation going on for you. Okay, so 3 operations times 3, which is 9 transformations you have to apply, or 9 operations you have to apply for a simple triangle. Now for a simple triangle, this is really easy. I mean, this is not a problem, is it? Now here comes a problem when you have huge object of 100,000 or 200,000 triangles. Imagine this, an object with 200,000 triangles. You are trying to perform those 3 operations. First you do translation, then you do scaling, then you do rotation. You are doing 300,000 operations just to rotate, translate, and scale 200,000 triangles. Actually, 2 times 3 is 600, sorry about that. So 600,000. Alright, so 600,000 operations. It's kind of actually too much. So what people do is they start utilizing matrices. And matrices has a very beautiful property. They say, okay, if we would like to do 2 operations at once, we could actually merge them. If you multiply 2 matrices together, you will merge those results into one big matrix. Okay? Now how this is even possible? Let's take, for example, the rotation and scaling. So if I grab a new matrix, sorry about that, just it's a little bit glitching here again. Okay, let me switch to another color here. Let me grab another layer. And they say, okay, we'll define a new matrix which is going to have, let's say, rotation. I would like, let's talk about this point for now. So I'm gonna actually take out what I want here. So this, sorry, okay, this is the point which I would like to transform. I would like to rotate, okay, and I would like to rotate it, let's say, to this direction, and I would like to scale it at the same time, okay. So if I rotate that point and scale it, I will get a point somewhere here. This point, that point, oh man, glitching in an amazing way. So this point will being transformed and exist right at that place. Okay, so they say, okay, you would like to rotate in 90 degrees and scale twice. So our transformation here for rotation was cosine, hang on a second, cosine of 90 degrees. Oh man, oh, sorry about that, just a second here. Okay, cosine of 90 degrees minus sine of 90 degrees, and here sine of 90 degrees, and here cosine of 90 degrees, okay, and we need to multiply it by this scaling matrix, which is going to be scale in x, nothing in y, oh, nothing in x here, or nothing in y in on the y part. So this is x, this is y. I will actually show you in a second the meaning of these rows, and nothing here and 1 here. Okay, so I would like to scale in x and y at the same time. Okay, so imagine these are the 2 kind of vector merged, if you know what I mean. 2 vectors has been merged. So you got the scaling in x and scaling in y only. Okay, imagine them as they have just been merged together into one matrix. Okay, now we have to multiply those 2. Okay, now let's get our numbers straight here. So we already said that cosine of 90 degrees is 0, right? Sine of 90 degrees is 1. Minus sine of 90 degrees is sine of 90 degrees is 1, minus is going to be minus 1, and cosine of 90 degrees is 0, and we got that. Multiplying by this matrix, 2, 0, whoopsie, 0, 0, and 2, and there we go. Now, what would this resolve to? Actually, I ran out of space apparently. Apparently, I was really at the edge. Okay, I'll move it. Oh, I'm even running away from the vertical space, but it doesn't matter. So we're gonna get a new matrix. So multiplying two matrices, you get a new matrix. So okay, so 0 times 2, 0 times 2 plus minus 1 times 0, minus 1 times 0, and this is, hang on a sec, let me just erase this, and this is my first term, okay, and then, oh man, 0 times 0, oh boy, plus minus 1 times 2, minus 1 times 2. Let's hope that I got my math straight. Now this is my second term, okay, which is going to be equal to something much shorter right now. Now we go to the bottom point, I think. So 1 times 2, 1 times 2 plus 0 times 2. Oh, hang on a second. What did I do here? 1 times 0. Sorry about here. 1 times 0. This is my first term. Second term. 1 times 0 plus 0 times 2. Okay. Now let's see here. So 0 times 2 here, oops, sorry about that. So 0 times 2 here actually goes to 0. And 1 minus 1 times 0 is actually going to be 0 anyway. So our first term is going to be 0. Okay. 0 times 0 is going to be actually 0. And let me accept that. And minus 1 times 2 is going to be minus 2. So minus 2. Here, 1 times 2 is going to be 2 plus 0, because 1 times 0 is 0. So it's going to be 2 plus 0 is going to be 2, which is going to be 2. And 1 times 0 is 0, plus 2 plus 0 times 2 is going to be 0. So we have this final matrix, which is kind of weird matrix. Anyway, let's hope that I really didn't make a mistake in the math. If I did, you have to really excuse me. I have to actually revise this again later, so I didn't miss anything. Now, let's get on of transforming this point. So I will get my matrix, my new matrix. Actually, let me put this in a little bit better order. I'll put here 1 and 0 times my new matrix, which is 0 minus 2 to 0. 0 minus 2, 2, and 0. Okay, didn't make a mistake there. Is going to equal to, and I'm going to put this right here. When you multiply a vector by, actually let me undo this because we need a little bit more space here. When you multiply a vector by a matrix, you get actually a new vector, you get a new position. Okay, so 1 times 0 plus 0 times 2, or actually plus 0 times minus 2, and then, oh, hang on a sec. 1 times 0 plus, actually 1 times 0 plus 0 times minus 2, and then 1 times 2 plus 0 times 0. And let's see what we get. We get a new vector. Oopsie. 1 times 0 is 0. 2 times minus 2 times 0 is going to be 0. So we have 0 here. 1 times 2 is 2, plus 0 is going to be 0, which is going to be plus 0, which is going to be 2 plus 0, which is going to be 2. And this is our new vector. So our new position, when I multiplied this simple vector to this our merged complicated matrix which we made up, we ended up with a point that is at 0 on x and 2 on y. So we have successfully scaled and rotated a point all in one operation, just all in one step. So in one shot, you scaled and you rotated your 3D object. And all this is achieved by just simple two matrices multiplication. So I took two matrices, I multiplied them, and I merged their results together. So I merged their operation together when I multiplied them. And immediately, whenever you multiply any point by this matrix, you immediately get your point positioned according to the order of the multiplication of this guy, or of these two matrices. Do you guys understand this? Do you see the beauty of it? Guys? Okay, there's somebody still alive there. Yes, Almir. Basic rules of trigonometry and matrices, and it's really and it's really like very straightforward. I mean, it's really like very straightforward. There is nothing convoluted or weird in that matter. The only thing which the weirdness will come when we start adding different dimensions, and I think I will keep that talk maybe for I will keep that talk maybe for another lesson, because adding the dimensions for rotation, especially for solving the problem of translation, because translation cannot be solved that way. Because you see, in order to merge the matrices operations, you really need to multiply. However, with translations, you have to add, because translation is an additive operation by its nature. So right now we get into problems which we're gonna talk about how to solve them in the next lesson, hopefully. Okay. Which is going to be recorded as well, because so we can. So I'm actually gonna in the next lesson I'm gonna be talking about, in the next online consultation actually, I'm gonna be talking about resolving the matrices for translation and how we can merge this all into one picture. Talking about the transformation and rendering pipeline, rasterization process, depth buffering, and lighting as well. So this is going to be all covered in the next lesson. This is how the theoretical part of the exam gonna look like. Actually, this is most of it is yeah, more likely it is, more or less. But okay, but how about this? Because we are still recording here, are there any questions related to the topic which I was talking about? And then I'm gonna answer all the other kind of specialized questions later, after the recording, after I stop the recording. So Okay. All right. All right. So since there are no questions regarding what I've covered here for today, I will stop the recording right now, and in the next lesson, as I already said, we will be covering translation, matrices, adding different dimensions, rendering and transformation pipelines, rasterization, and depth buffering afterwards. All right. So thanks a lot for your attention, and see you then in the next lesson.